What you see here is the image of the first computer ENIAC. This giant is about 2.4 meters high, and it occupies more than 160 square meters. The basic computing element of ENIAC is called a vacuum cube. It is hard to imagine people in the 40s. Us are more familiar with these types of computers. They are small, light, and fast. So we may wonder what happened. If you take a look at the core computing element, instead of a large vacuum cubes, you see a small highly integrated chip called a microprocessor. If you zoom in the microprocessor further, you will see these tiny little lines standing in a certain layout. The smallest distance between these lines is called a node. The computational power of a computer is largely determined by how small the node is, because the smaller the node, the more lines can be put onto a single microprocessor, the more powerful the computer can be. In order to fabricate these small lines, we need a process called optical lithography. It basically involves several main components. The light source, which emits short wavelength light. A mask, which predefines the pattern of the lines you want to fabricate. A lens, which demagnifies the pattern from the mask. And a wafer with photoresist on it for the final layout of the pattern. The laser light from the source illuminates the mask, and the pattern is projected onto the photoresist. In this way, one can fabricate those small lines in a microprocessor. Like mentioned before, the smaller the node is, the more powerful the computer can be. For a given lithography system, the smallest distance between the two lines is defined as the resolution of the system. The resolution is proportional to the wavelength lambda. The shorter the wavelength, the higher the resolution can be. In order to increase the resolution of the optical lithography system, the wavelength is decreased from 400 nanometer all the way down to 193 nanometer. Of course, this process of using shorter wavelength can be continued for the fabrication of smaller node. One can use EUV source or even X-ray, for example, but these systems are very expensive, and what is worse, there is no lens currently available for X-ray, so other methods must be developed to further increase the resolution without using shorter wavelength. One of the promising techniques is called double patterning. It involves two steps to define the structure. In the first step, one exposes the photoresist where the resolution can be achieved. In the second step, the pattern defined in the first step is shifted a little. After this, a second pattern is defined. In this way, the node size can shrink into half of the original one. One of the prior conditions for the successful implementation of this scheme is to have very precise control over the displacement introduced in the second step, which is known as the overlay problem. Because the overlay can be even smaller than the resolution, it is very technically challenging. Require node for each computer generation, which is also known more generally as the Moore's law. The next step is 10 nanometers, which means if we want to use double patterning for future fabrication, the displacement sensing beyond this value should be achieved. To encounter this overlay problem, we proposed a new scheme by the combination of singular beam and resonant nanostructures. Normally, the beam from the laser source follows a Gaussian distribution with a maximum intensity at the center and decreases smoothly to the side. However, the beam we use has a singularity point at the center, which means there is no light at this point, and it is also called a singular beam. One can imagine if a small structure is illuminated by this singularity center, no light would be scattered, but once the structure is displaced from the center, it scatters light, and one can measure the scattered light distribution to extract information about the displacement with respect to the singularity center. The structure we choose is composed of 2 nanorods. Because of the resonances involved, the power ratio defined by the power scattered to the left and right can be extremely sensitive to nanoscale displacement of the 2 nanorods. Our calculations showed it is very promising to use this system to detect nanoscale displacement, which is directly related to the overlay problem. If you want to know more information about our method, please have a look at our published paper. Thank you for watching this video and I hope you enjoy it.